Hello, my student ID is 105028030. We'll be talking about the Secure Sockets Layer, which is the SSL protocol. The SSL protocol encrypts internet communications and guarantees secure transmission of data between a client and a server. It aims to provide privacy of communications over the internet and data integrity. And it was introduced because of the widespread use of the internet globally, which resulted in the need to safeguard confidential communications sent over this open network. The SSL protocol was the first protocol developed for this objective by Netscape Communications, but it was, however, considered obsolete due to its security weaknesses. And the Internet Engineering Task Force recommended its abandonment and later released the Transport Layer Security Protocol, which has better security features compared to SSL. History of the SSL protocol. It started with the SSL 1.0, developed in 1994, but it was never publicly released due to critical security flaws. Then the SSL 2.0, released in 1995, it was the first public release of SSL. However, this version also had several security flaws. SSL 3.0, released in 1996 to primarily fix the security flaws in SSL 2.0. And because of these critical security weaknesses, there was need to develop a better security protocol. This led the IETF to develop the Transport Layer Security Protocol. TLS 1.0 was released in 1999 as an upgrade to SSL 3.0. TLS 1.1 released in 2006 as an upgrade to TLS 1.0. TLS 1.2 released in 2008 as an upgrade to TLS 1.1. TLS 1.3, which is the current version of TLS, was released in 2018 and it introduced significant changes to streamline the protocol for better performance. Structure of the SSL protocol. SSL and TLS protocols are located at the session layer, which is layer 5 of the Open Systems Interconnection model, which is the OSI model. SSL protocol has two layers, handshake and record layers. And the record is at the lowest level, which is just above the TCP protocol. The handshake layer contains the handshake protocol, which allows the server and client to authenticate to each other, negotiation of encryption algorithms, the exchange of encryption keys. The change cipher specification protocol, which signifies that the client and the server are ready to communicate in an encrypted environment. And this protocol is used to change from an insecure to a secure environment. And the alert protocol, which signals error messages. The record layer contains the record protocol, which allows fragmentation of data, whereby data is split into multiple blocks of certain bytes of length if it exceeds a specified limit. It allows compression of data before encryption. It allows the message authentication and integrity over compressed data. It enables encryption of application data using symmetric encryption. And this is a pictorial representation of the structure of the SSL protocol as explained. Then we have how the SSL protocol works. When connecting to a secure website using SSL, the standard HTTP using port 80 changes to HTTPS using port 443, and a padlock is activated indicating that the browser connection to the server is secure and transmission of data between the client and the server is encrypted. The SSL connection is established between the client and the server using the handshake process, which begins with the client hello, where the client and the server exchange information necessary to determine connection properties. And such information includes the client version, which is a list of SSL versions it supports, beginning with the latest one, which is the most preferred. The client random, which is a 32-byte random number. The session ID, which is the one used for the connection. The compression method, to be used to compress data before encryption. The cipher suits, which is a set of cryptographic algorithms, and which are identified by strings, and the client sends a list of all cipher suits it supports in order of preference, and the extensions, whereby the client requests extra functionality for the connection by extensions. Then we have the server hello, which responds by either containing the information based on the client hello, or it may be a handshake failure message. So the server hello may contain information such as the server version, which selects the preferred SSL protocol version from the client's list, the server random, which is a 32-byte random number. The client random and the server random are used to generate the encryption key. The session ID, if the client session ID is not empty, the server searches the prior cached sessions and resumes that session if there is a match. If it was empty, a new session is created by the server and sent in the server session ID. Compression method, the server chooses the compression method from the client list. The server also selects a cipher suite from the client's list. And if requested and the server has capability, it will provide the extra functionality for the connection via extensions. Then we have the server certificate, where the server sends to the client a signed SSL certificate proving its identity and enclosing its public key. Then the server may also require the client to provide its signed certificate, but this is optional and occurs scarcely. And we have the server key exchange, which is only sent if the server certificate is insufficient for the client to exchange a pre-master shared key. And we have the server hello done, which confirms the end of the server hello message. Then once the client server hello message is done, the client key exchange stage is whereby the client creates the pre-master secret key using the selected cipher suite. It then encrypts it via the server's public key, which ensures that only the server can decrypt the key. And on receipt, and sends it to the server, and on receipt of the pre-master secret key, the server uses its private key to decrypt it. The client and the server generate the master secret key based on the client random and server random exchanged earlier. And the master key is usually 48 bytes in length, and it's used by the client and the server to generate session keys, which are symmetric keys to encrypt and decrypt data during the SSL session and to verify message authentication and integrity. Then we have the client change cipher specification, where the client signals that it's ready to switch to a secure environment and that future messages will be encrypted using the session key. And after that, the client sends the handshake finished message to show that the handshake process is finalized on their part. And this is the first encrypted message of the secure connection. And the server, vice versa, also confirms that it's ready to switch to an encrypted environment using the server change cipher specification. And it will also send the server handshake finished encrypted message to the client so that the handshake process is finalized on their part. So once this is done, the handshake process is essentially complete. The SSL connection has been established, and consequently the session can now commence, whereby the client and the server communicate privately using the symmetric keys, which will enable them to encrypt and decrypt data and verify message authentication and integrity. And if either of them negotiates the SSL connection, perhaps due to user intervention, the process will repeat itself. I'm now going to demonstrate this process on Wireshark. I'm just going to minimize this, open my command prompt, and this is just to confirm my IP address. So I'll just type in my IP config, and my IP address is this one, 10.65.40.75. I'm now going to minimize this, open Wireshark. I'm using the wireless, so I'm just going to click on Wi-Fi and wait for it to start capturing traffic. There we go. I'm just going to go to my browser and enter a secure website, for example www.ecu.edu.au. And we know that this website is secure because it has the padlock is activated, and we can see that if you click on it, you can see that the connection is indeed secure. So I'm just going to close that, go back to Wireshark, stop capture. Then on the display filter field, we're just going to filter the SSL protocol. And in this case, we can see we're using the the TLS version 1.2. I'm just going to start from the client hello, which is where the handshake process begins. You can see my source IP is 10.65.40.75, destination is 13.107.136.9, protocol is TLS version 1.2, and we have the client hello. Just going to go here at the bottom so that we can view the contents of the client hello, and you can see that it contains the version, which is TLS 1.2, the client random, the session ID, the length is 0, so in this case it's empty. The cipher suits, and we have 19 of them in the length. Compression methods, one method, the length, and the extensions requested by the client. We're just going to go here to the server hello so you can view the same. And you can see the server hello contains the version, which is TLS 1.2, the server random, the session ID, the length has been given now is 32, and the session ID has been included, the cipher suit, which is identified in a string, and it shows the TLS, which is the protocol, the ECDHE, which is the key exchange algorithm, the RSA with AES 128, GCM, which is the data encryption algorithm, and you can see the SHA 256, which is the message authentication code. The compression method is null, which is 0, and the extensions which have been provided by the server as requested by the client. You can also view the server certificate, and the type is certificate 2, and its length, certificate's length is given here, and we can also see the status of the certificate and the status type. I'm just going to go further down to view the server key exchange, and in this case it was necessary. The type is server key exchange 12, and you can see the length and the Diffie-Hellman, which denotes the key exchange, and the server hello done, which signifies the completion of the server hello message. I'm just going to go here and click on the client key exchange. The client key exchange, you can see the version here is TLS 1.2, the length. We can also see the client key exchange here, the type is 16, the length. You can see the key exchange Diffie-Hellman as well, and see the client change cipher specification protocol, and the type is that 20, the version is TLS 1.2, the length, and the message. And you can also see the client handshake finished message, which is the first encryption message for the secure connection, and it's encrypted. And you can see the type, the version, the length, and you can just go to the next thing so we can view for the server. This is the server change cipher specification protocol, and you can see the same contents, and you can also see the server handshake finished message. If you go further down, you can see the application data, which is what the data we're actually encrypting. You can see it's HTTP over TLS protocol. The version is TLS 1.2, the length, and the data is encrypted. So Wireshark enables us to view all the steps necessary for establishing an SSL connection using the handshake process, and I've explained the same. The importance of the SSL protocol is mainly for communications, privacy over the internet, and to ensure the integrity of data. And it's very important in our use today, in today's internet-focused world. With that, I'll just end. That is the end of my presentation. Thank you.